Look at this leaf. At first glance, it's just a beautiful pattern. But what if I told you there's a hidden story here? Could it be a secret code whispered by the very geometry of nature? It's a window into a secret language of the universe, spoken in repeating shapes, in infinite detail. The world of fractals. From lighting, pine cones to snowflakes, they are everywhere in nature. Fractals are mathematical sets, or shapes, characterized by self-similarity, meaning they exhibit similar patterns at different scales. Fractals are characterized by their infinite detail and can be found in both natural phenomena and mathematical constructions. Paying close attention to the surrounding, you will realize that nature is a fractal artist. From the grand scale of coastlines carved by the relentless ocean, to the delicate branching of a single frost crystal, these self-similar patterns appear again and again. Why are these patterns everywhere? Because fractals are often the most efficient and robust way for nature to build complex structures with simple rules. Tree branches spread out to maximize sunlight capture, and each smaller branch mimics the structure of the whole, ensuring every leaf gets a share. It's an elegant, economical design principle at play all around us. While nature has been using fractal geometry for eons, it wasn't until relatively recently that humans began to truly understand and formalize this language. Mathematicians like Benoit Mandelbrot in the late 20th century gave us the tools to describe and explore these infinitely detailed shapes. Before the term fractal was coined, mathematicians encountered strange and paradoxical shapes that didn't fit the smooth, regular world of traditional Euclidean geometry. These were often dismissed as mathematical monsters or curiosities, but they laid the groundwork for a new way of thinking. During the 17th century, Gottfried Leibniz, the co-inventor of calculus, pondered the idea of recursive self-similarity. The true foundational work began in late 19th century. In 1872, Carl Weierstrass presented a function that was everywhere continuous, but nowhere differentiable. It is a curve with infinite detail that could not be described by a traditional tangent line. This challenged the very notion of a smooth curve. In 1883, Georg Cantor introduced the Cantor set, a counterintuitive set of points on a line created by iteratively removing the middle third of each segment. This was one of the first explicit examples of a self-similar set with a fractional dimension. In 1904, Helge von Koch created the Koch snowflake, an infinitely long curve that encloses a finite area. It's a perfect example of a shape whose perimeter grows endlessly with each iteration. Wachwa-Sierpiewski in 1915 constructed the Sierpiewski triangle and Sierpiewski carpet, which are prime examples of fractals with non-integer dimensions. Gaston, Julia, and Pierre Fatou in 1918 explored the iterative behavior of complex numbers, leading to the discovery of what are now known as Julia sets. The scattered threads of fractal research were finally woven together in the 1970s by Benoit Mandelbrot. Mandelbrot is a Polish-born French-American mathematician working at IBM. He believed that traditional Euclidean geometry was a poor way to describe the irregular shapes of the natural world. In 1975, Mandelbrot coined the term fractal from the Latin word fractus, meaning broken or fractured, to describe these shapes. He defined them as sets with fractional dimension. With access to powerful IBM computers, Mandelbrot was able to visualize the work of Julia and Fatou. His most famous contribution was the discovery and visualization of the Mandelbrot set, complex mathematical shape that serves as a map of all the Julia sets. This set became an icon of the field and demonstrated the infinite complexity that could arise from a simple formula. The Mandelbrot set is certainly the most popular fractal, and perhaps the most popular object of contemporary mathematics of all. In the mid-1980s, like Walkman cassette players and tie-dyed shirts. The bug-like silhouette of the Mandelbrot set was everywhere. The Mandelbrot set had become a symbol, represented the need for a new mathematical language, a better way to describe the fractal nature of the world around us. The seemingly abstract world of fractals has surprisingly practical applications that touch our daily lives in countless ways. Look at the compact antenna in your smartphone. Its intricate design is often based on fractal geometry. A single fractal antenna can operate efficiently across a wide range of frequencies, eliminating the need for multiple antennas in one device. This is due to the fractal structure, which resonates at multiple wavelengths simultaneously. Do you wonder how the breathtaking landscapes in your favorite fantasy movie or stunning digital images and animations with infinite detail are created? They are all generated using fractal algorithms. Fractal algorithms are used to create believable, detailed landscapes, including mountains, coastlines, riverbeds, and clouds, for films, video games, and virtual reality. The self-similar nature of fractals naturally mimics the irregularity and detail of these natural formations. Even the way doctors understand the intricate network of blood vessels in your body relies on the principles of fractal branching. Fractal analysis of blood vessels can help in the diagnosis of diabetic retinopathy and the early detection of cancerous tumors, which often have a higher fractal dimension due to their chaotic growth. Fractals provide a powerful framework for understanding and modeling complex, seemingly chaotic systems, such as weather and climate, geology, and finance. The patterns of clouds, coastlines, and turbulent fluid flows exhibit fractal properties. The fractal market hypothesis suggests that financial market price movements exhibit a fractal nature, meaning that patterns repeat over different timescales. Traders and analysts use fractal indicators and technical analysis to identify potential reversals and trends. Architects are incorporating fractal patterns into building facades and structures to create aesthetically pleasing and functionally efficient designs. From more efficient technology to more realistic virtual worlds and even advancements in medicine and finance, fractals are a powerful tool shaping our modern world. So the next time you're walking through a park, or even just looking at a head of broccoli from the local shops, take a moment to appreciate the hidden mathematical beauty within. Fractals are a reminder that even in the seemingly chaotic and complex world around us, there are fundamental patterns and elegant rules at play. They show us that there is a deep connection between mathematics and the natural world, proving that math is indeed the language of the universe. What other hidden mathematical wonders do you think are waiting to be discovered? Let us know in the comments below. Thanks for watching today. I hope you learned something new. Don't forget to like this video and subscribe for more math explorations into the fascinating world around us.